well, I'm thinking really clearly right now, between the electrical components and the mass on a spring components. So last time we talked, we discussed how the electrical components in an electric circuit are going to be, you have something that looks like L Q double dot, so that's the acceleration of the electric charges, plus the resistance times Q dot, that's the resistance to the electric current, plus 1 over C times Q, which is the charge on a capacitor, is equal to the voltage as a function of time. So this presumably would be a function of time because all of these things are related to time. And we compared this to mx double dot plus like b x dot plus, that's a dot. And a dot is a time derivative. So that's like, this is acceleration, that's an acceleration, this is a velocity. And then we have a plus kx. K is a spring constant, is equal to the force that's acting on something. Okay, so we saw these two things. Now, let's take a look at what each of these terms are. So a spring is the resistance to displacements. A spring provides a resistance to displacements from an origin. This term here, this friction term, that provides a resistance to motion in a given coordinate system. So friction is a resistance to motion. This is a resistance to displacement. This is a resistance to motion. And the mass here, or I should say this term, that K, that factor, the factor of K is a resistance to displacement. This B, or sometimes beta, or a whole bunch of other alternative letters could go in here, is the resistance that you have, so it's friction basically. It's an encapsulation of friction. That's resistance to velocity. So this is a resistance to displacement, this is a resistance to velocity, and this one, M, is a resistance to accelerations. So the inertia, or the mass of an object, is the thing that resists the acceleration. And that's why you have the original formulation of Newton's second law, or like the first order. If you assume that the mass stays constant, then you get F equals ma, or F equals mx double dot. It's forces that cause masses to accelerate, and the larger the mass, the smaller the acceleration will be for a given force. And so this is the resistance to accelerations, is the mass. The inertia is the thing that prevents you from moving something around. So that's what's going on here. Now, if we look at what's happening in with electric charges, this capacitance, a capacitor, which is those two parallel plates, like you have a wire coming in like this. So here's this wire, it's broken. You have two plates that whereupon you can accumulate electric charges, positive and negative electric charges. And these things are the capacitance, or 1 over the capacitance, gives you the resistance to separating charges. Capacitance actually means that it's easy to separate the charges. So 1 over the capacitance means that it's difficult to separate the charges. How much charge you accumulate on the capacitor is this term here gives you the resistance to that, how much energy it takes to fill a capacitor. So this is the resistance to building up electric charge, which is a displacement of that charge from a neutral condition. This R here is the resistance, like in terms of ohms, like the resistor that you would have. The size of the resistance tells you how much you resist the motion of those charges, which is exactly the same thing we have here. This thing resists the motion of an object through some space. This resists the motion of charge through some wire. And here the inductance is the resistance of changing the rate of the current flowing, changing the current. Just like this one is a resistance to changing the velocity. So it resists acceleration, it resists changing the velocity. The inductor, which is the coil of wire, resists a change to the electric current. Once you get an electric current going, you're going to actually build up a magnetic field in here. And if you want to change the direction of the current, then you have to first dissipate the energy in the magnetic field and then realign everything. And so the more energy is built up in the magnetic field, the longer it will take to dissipate that magnetic field, and the harder it is to change the current. And so Q dot is the current, and so Q double dot is the change in the current. So it's hard to change the current, and the stronger the inductance is, the harder it is to change the current. And so that's all these things relate to each other, or there's an analogy between the two, and the analogy has to be there because it's the same equation, just spelled differently. So that's kind of cool. All right, now a few other things. Let's consider AC circuits for a moment. So AC circuits, instead of having a battery plugged in, what you have is an oscillator. So you have something that's wiggling the electric field, wiggling the voltage up and down and up and down and up and down. And you can plug that into something that looks like this. Okay, so we have an AC circuit now connected to a capacitor, where before we had a DC circuit and you would build up the charge on the capacitor like this, and this charge would build up like that. But here, an AC circuit, what we want to look at is what is the response of this circuit here? What's the response of this voltage, or like the behavior of this element, this capacitor, when you oscillate the voltage? So you're flipping the voltage up and down at some frequency. So what we want to plot is basically how does this thing behave? Maybe the energy is stored in it as a function of the frequency that we oscillate. So it's this frequency right here. So in particular, we're going to divide it into two things. We're going to divide it into high frequency, the response at high frequency, and the response at low frequency. And then there's going to be a transition in between the two. So with AC circuits, if this is a really low frequency, it's almost like a direct current. Okay, if it oscillates once every year, then for most of the year it behaves like a battery with a direct current, with the positive voltage here and negative voltage there, and then 6 months later those signs will switch. So at very, very low frequencies, this acts like an open in the circuit, and so you're going to build up charge, and then as it switches back over, these charges are going to dissipate, and then it will build up charge in the opposite direction, matching this right here. So the response of the voltage that you get across this capacitor compared to the voltage here in your AC circuit. So this is going to be some number of volts AC. So if you're in the United States of America, you might have 120 volts AC like this. Or if you're in Europe, I think it's 240 volts. Anyway, so they all have different things. Maybe in the United States it's 110. I don't know what it's either 110 or 120. It doesn't really matter so much. But anyways, you'll have some height of the voltage, and this is the ratio of the voltage across, like how much the energy drops across the capacitor compared to how much the energy drops across the power supply. And so here it's 1-to-1. If you go really slow, then the capacitor is going to exactly match the voltage, and as it switches signs, then it will also switch signs with it. Okay, so there's a question here, which is what state of matter is electricity? So electricity isn't a state of matter. A state of matter is how are the electrons and the protons that make something up arranged. Electricity, well, so it depends on what you mean by electricity. So the electromagnetic field is the field that responds to the presence of electrical sources like electric charge. And it has the mediator, or the particle that instantiates the electromagnetic field, is the photon. So you have a proton or something like that, has an electric charge, and it creates a photon field around it, or it disturbs the electromagnetic field around it. When you wiggle that electromagnetic field, those vibrations are called photons. So the way that quantum field theory works is that you say, okay, I have a field, and here's my field, and the field is there. And if you vibrate that field, those vibrations are called, that's what we call the particles. So if you have an electron field, and then you vibrate the electron field, those vibrations are called the electrons. And for the case of the electromagnetic field, you have an electromagnetic field, you vibrate the electromagnetic field, and those vibrations are called the photon. Okay, and the way that you vibrate the electromagnetic field is that you take something that couples to that electromagnetic field. So you take something that that attaches to the electromagnetic field, and then you wiggle it, and it will vibrate the attached electromagnetic field and create those photons. So the same thing is true like with gravitational radiation. You take something that couples to space-time, so something that has mass, have something that couples to space-time or something that couples to the gravitational field, and then you wiggle it. And because it couples to the gravitational field, it will cause a distortion in that gravitational field and send out radiation in the form of gravitational radiation. So the same is true with electromagnetism. The same is true with the strong force. You take a cork that has color charge, and then you wiggle the cork, and those vibrations in the quantum chromodynamic field, the color field, are what form the gluons. Okay, so anyways, here, this is a 1, this is 1. So when you're operating at low frequencies, the response on the capacitor is exactly equal to the response from your power supply. At super duper duper high frequencies, what's going to happen? At very high frequencies, this acts like a short because it never has time to build up any charge. So like charges will start flowing, okay? But by the time you try to build up charges on here, your power supply is already going in the opposite direction. And so it's, as you try to build up charge, by the time you have any opportunity to build up charge, you're already drawing that charge back down and putting it over on this side. And then as it piles up over here, you're already drawing it back and sending it back the other way. So the capacitor never has time to respond if you're wiggling it too fast. The analogy would be, so let me go to the camera view so that I can show, well, just for no good reason, we're going to go to the camera view. So here's the camera view. If I have, I need to have a pendulum of some sort. What's a good pendulum? Okay, here we go. We're going to use this. Okay, so that's not a very good one. I got to have a better pendulum than that. All right, here we go. This is a good pendulum. Okay, so here's my pendulum. I've got it like this. The question is, what is the ratio of the response of this pendulum if I oscillate it from the top? Now, if I oscillate very slowly, you can see that the pendulum displaces itself exactly as far as my hand displaces the top of the pendulum. So it's always directly underneath my hand. And so that's a one-to-one response. I move it this way, and I get a response. I move it this way, I get a response. That response is exactly the same size. Now, I can have it oscillating so that even a small, so here you can see that my hand is not moving very much, but the pendulum is moving a lot. Okay, so that means that the response would be very large. So this is not a ratio of 1-to-1. This would be a ratio of like 10 or 15-to-1, something like that. Now, if I go very, very fast, if I wiggle the top very, very fast, then you'll see that the pendulum is not moving very much at all. So there's the pendulum. I wiggle it very fast, and the pendulum actually is just kind of sitting there. There's hardly any movement of the pendulum. The same thing is going on here. When I have very high frequencies, this never has the opportunity to build up any electric charge. And because it never has the ability to, oh, how about if I switch back to the camera that I was looking at? What a great idea. All right, so because this never has the opportunity to build up any electric charge, the voltage across that goes to 0. So what you're going to get from this circuit is something that looks, well, it's going to do, like mystery stuff happens here, and then it's going to decline like that and go down to 0. It will eventually go down to 0. Okay, it might have a peak or something like that. But anyway, the point being that at low frequencies, you get a unit response that it exactly matches, and at high frequencies, you get no response at all. Super high frequencies, there's no response. And then everything in between has to smoothly transition from one to the other. So that's with a capacitor. With a resistor, if we look at a resistor, there's basically no difference on a resistor. So like here is your thing, here's a resistor. The resistor is going to resist what it's doing no matter what. And so there's the voltage across the resistor is going to not have a response the same way that a capacitor does, because you're not building up charge, you're just dissipating energy off of the resistor. Okay, so here's a question. Never mind, it's not a question, but it is a statement that my pendulum is the best pendulum ever. All right, so the last thing would be this inductor. Okay, that's the important thing about this inductor. So here's our AC circuit. We go like this. Here is an inductor coming off like that. Okay, now the inductor is just a wire. It's coiled. It has a unique topology, or an interesting topology, but the wire itself is just a coil of wire. So what's going to happen here if we look at the voltage? So this is the voltage response to what I have there. And again, unit response would be that the voltage matches, the voltage drop across the inductor, so measured across this, would exactly match the voltage across my power supply. And again, we have low frequency here and high frequency here. Okay, so what's going to happen? Well, at very low frequency, we don't have to worry about the time that it takes to build up and dissipate the energy in the magnetic field that we produce. So we're oscillating very, very slowly, and this acts just like an open wire. We're not worrying about the relatively negligible effect of dissipating or producing the magnetic field that's in there, because we're doing it very slowly. And so we don't have to worry about the time scale that it takes to change those things. And so as a consequence, at low frequencies, the voltage drop across this, it's just a wire, it's a short circuit. And so the voltage is going to be 0 at low frequencies for an inductor. Okay. On the other hand, if we try to oscillate this very, very quickly, what's going to happen is it's going to try to switch back and forth the magnetic field, and it's going to resist that change of the magnetic field. So it tries to resist that change, which means that you're going to get a response here that exactly matches the voltage, except it turns out that it's exactly opposite the voltage. We're not going to worry about that. We'll just worry about the absolute value of this voltage. So as this thing oscillates, as our power supply oscillates, if it's oscillating at high frequency, then there's no current that flows through this inductor, because all of that energy that goes into it is going into changing the direction of the magnetic field, and no current is able to flow through the inductor. So you get a large voltage drop across it. Okay, so at high frequency, then you get a voltage drop that matches your power supply. And so that comes up to 1. And so with an inductor, you're going to get something that looks like this. At low frequency, there's no voltage drop at all. It acts like a short circuit. And at high frequency, it resists all change because the inductor is like a mass. And so if you try to oscillate a mass very quickly, you get very little displacement. So that is the inductor and the capacitor act exactly opposite to each other. The capacitor at low frequency acts like an open in the circuit, like no current can flow at all through the capacitor. Where an inductor, that same situation applies, where there's no current that flows through the inductor at high frequencies. So capacitor has this response for low frequencies. The inductor has this response at low frequencies, where the capacitor has that response at high frequencies. So they behave exactly opposite each other. One of them resists low frequency oscillations. The other one resists one of them resists low frequency oscillations. The other one resists high frequency oscillations. Okay, so this allows you to build stuff with these things. Now, when it comes to resistors just resist the flow of electricity regardless of how fast it's happening. So this allows you to build stuff. For example, suppose that you have a power supply with all sorts of stuff, okay? And it could be from a variety of different sources. And suppose that you have some piece of machinery right here. So here's your machine. We'll draw it like that with a smokestack, even though it's an electrical machine, but here's our machine, okay? And we want to power this machine. However, if this machine has a particular characteristic where it can only operate at low frequencies, so you have all sorts of frequencies that might be coming into that machine, but it needs to operate at low frequencies. Like the power supply has to be, the change in the power has to be at low frequencies. You can't have high frequency changes, because if you have high frequency changes, then it will cause some kind of disruption. So you have this machinery that you need to allow only low frequency power to get into it. Then what you do is you put across this, if you want low frequency, then what does that mean? That means that you want low frequencies to pass and high frequencies to be disrupted. So low frequencies to pass means that you would put a capacitor across it like this. Okay, so you put a capacitor across it. That way, at low frequencies, you're going to build up a voltage. This will work at low frequencies. You build up a voltage here. Let's see, did I do this right? No. So if you want low frequencies to pass on in this direction, then what you have to do is put in, I think I did this backwards. All right, so we're going to work through this together. It's going to be amazing. I want low frequencies to I'm going to allow 2 different paths for my electricity. So the electricity can come out of my power supply, and it can either take this path there, or the electricity can take this path over here. The way that you force the electricity to go down one path or the other is that you restrict the flow of the current through one path or the other. And in particular, we want to control the current through this one that allows whatever is left over to make it through the other direction. So let's say we have this machinery that wants to operate at low frequencies, which means that if there is a low frequency, we want no current at all to flow through here. So at low frequency, we want no current to flow, which is indeed what I said before, that we want a capacitor right there. So I did get it right. So if you want low frequencies to operate your machinery, then if you put a capacitor here, low frequency is going to prevent the flow of current through here. So it's going to build up electric charge. No current can flow through it, which means that all the current is going to flow this way through your machinery and back that way. And when it switches directions, you, again, fairly quickly build up your supply of electric charge, except now it's pointed in the opposite direction. And that forces the current to flow this way, because the current can't flow through this gap, right? All you can do is fill up the capacitor. You can't fill up, there's no current flowing through the gap. That's like an air running through the gap. So you put this capacitor in, and now your machinery operates only at low frequency. It forces low frequency electricity supply to go through your machine, which is what you want. On the other hand, suppose that you have a different piece of machinery where you want the high frequency to go through. So I set up an electric circuit like this. I have a new piece of machinery. Okay, this one is a happy piece of machinery, and it only operates at high frequencies. So you want to send high frequency power through it and not low frequency. So what's basically going on here is you can imagine all sorts of noise. So you have like an antenna or something like that. You're picking up signals from an antenna, and you want to filter out the low frequency noise. The low frequency noise could come from 60 hertz from the wall. So you have a power supply in the wall. You have a very sensitive instrument that's picking up radio waves. You want to cut out all of the 60 hertz noise from the wall and only sample the 250 megahertz noise or signal that you're looking for. So you would put out a high pass. You put in a high pass filter that would eliminate the noise from the wall. Okay. So this is a high pass filter, which allows high frequency oscillations to pass through your system. Okay. So in this case, you would have your inductor like this. You send the voltage through. If the voltage is very high frequency, then that prevents current from flowing through here, and it forces current to flow through your machine. If, on the other hand, it's very low frequency, so it's oscillating very slowly, then all the current is going to flow through the path of least resistance, which is this coil of wire, and no electricity will flow that way. So you can build these kinds of electrical devices. You can couple these things together so that you can either allow high frequency stuff to pass or low frequency stuff to pass, and drive your machinery as needed. And another thing you can do is you can pick two elements. You can imagine setting up a circuit that looks like this. Here is my power supply. I have, here's my machinery over here. Okay, and now I have a capacitor here and an inductor here. And this acts like low pass, this acts like high pass, and then I tune them so that there's only a narrow band. So if the current is really, if the frequency of the oscillation of my alternating current power supply is fast, then all the current will flow this way through the capacitor. Or the electric field you'll build up the voltage. The current will flow through here as though it's a short, because it doesn't have time to build up charge in response. No current will flow through here because you have to dissipate the magnetic field, and no current will flow through here because this provides some resistance. Okay, so at very high frequencies, all the current will flow through the capacitor. At very low frequencies, all the current will flow through the inductor. And so you have a window where it's like, here's my frequency response, and all the current that's down here will flow through the inductor. All the current that's up here, like any frequency that comes into my system right here, any frequency that comes in will be filtered out by the capacitor up here. So it will all pass through the capacitor up there, which gives me a band, some narrow band, where it will go through my resistor. So you can choose your capacitance and your inductance so that you can narrow down the band that's accepted, the band that actually goes through your, say this is an amplifier or something like that. So you can choose these things so that you get very narrow band like this, and then you're only sensitive to some source that has a small bandwidth. And that's, I described this last time, but that's how a radio works, at least the old time radio. I think the new ones still work that way, but basically you have a variable capacitor, and that allows you to adjust the location of this frequency range where your system will be sensitive. So I can show you what a variable capacitor looks like, because it's kind of interesting to look at. A variable capacitor, they look like this. So on the inside they look like that. You can see all these metal plates, and those metal plates will interleave with each other. And the more they interleave, the more charge you can store in the device. So, and you notice that it's variable, so it has to have a knob. So there's your knob right there. Okay, and this is a really big variable capacitor. And then as you spin the dial, those plates will either interleave with each other or they'll pull out from each other. Anyways, they do also make variable resistors. I think they make variable inductors as well. But variable capacitors are the easiest, I think, to conceptualize. I think a variable resistor just, what do those look like? I haven't looked at those for a while. Resistor. It's like something slides along the resistor so that the electrical current leaves at some point in the middle of the resistor. It's kind of weird. Variable inductor. This I don't know. I mean, it's obvious that you can make them. It just probably takes an engineer a half an hour of thought to be like, oh, here's how you'd make one. But anyways, there you go, variable inductors. Okay, so that is electrical circuits and electricity in general. Now, let's talk about the different equations that would describe what's happening in these different situations, or at least with electricity in general. So one of the things that we found was that if you have an electric charge in some location, so this is a charge Q, that it's going to create an electric field emanating from that location or centered on that location pointing outwards. Okay, and then we showed that if you had some surface around that, so this creates basically a hill, creates a slope. This thing creates a slope in the electric field. The electric field is strongest right next to it, and it gets weaker and weaker and weaker as you go farther from it. So it's strong right here, weaker and weaker and weaker as you go out. So there's a gradient in the electric field from this source. There's a source and there's a gradient in the electric field. It would be like saying, okay, here's my electric charge, and the electric field, the strength of the electric field is strongest right next to the electric charge, and then it drops down as you go away from that electric charge. Okay, so how do you describe that in an equation? Well, you would say, okay, so there's a slope, and the slope of the outward pointing slope, in particular that it points directly outwards, okay, the outward pointing slope of the electric field is proportional to the charge density, how much charge you have here. If you have a lot of charge, then you're going to have a stronger slope that radiates away from that single point. Okay, this symbol here means the stuff radiating away from a single point, the stuff that's moving directly outwards. Okay, so that is one equation that we get from electric fields. If you have an electric charge in some region, it will create an electric field that points directly outwards. Okay, if, for example, there were some magical object called a magnetic north pole, so if you could have a north pole that was all lonesome by itself, a magnetic field, except this is just the magnetic north pole, not a magnetic field that is a north and south pole. So most magnets are like north and south pole, but you could imagine in your mind that you could just have a north pole by itself without a south pole associated with it. If that was true, then you would get, that would create a magnetic field. So here's your object that's a pure monopole, and it would create a magnetic field that points directly out from some location. And you would get the same thing. You would get that the production of a magnetic field squiggles the magnetic charge density. Okay, so if you had a collection of magnetic north poles with no south pole associated with it, you would create a magnetic field that points outwards in exactly the same way that the electric field points outwards. Okay, so this is another equation that describes the behavior of electric or magnetic charges in space-time, like in the environment that we live in. Turns out that there is no evidence for magnetic monopoles. Okay, as far as we can tell, an isolated magnetic north pole does not exist. It could exist, but as far as we can tell, it does not exist, or they're very, very, very rare. And as a consequence, this is always going to be zero. Okay, so we're going to make the approximation that it's always zero. It's possible that a magnetic monopole exists somewhere in the universe. It has not been found. So we will make the approximation that this is always zero because, as far as we can tell, the number of magnetic monopoles per, bazillions and bazillions of electric charges is zero. Like the ratio is essentially zero. So we get another equation that is that there are no magnetic monopoles, and so there's no way to source a pure north magnetic field. So that's a second equation. We have two equations that tell you basically what is the effect of a charge density of that particular thing. So an electric charge density produces an electric field that points directly outwards from that charge, and it needs to point directly outwards. The reason that it needs to point directly outwards is because there's no reason to choose a particular orientation, right? You should be able to rotate your head and see exactly the same electric field. There's no change to this if you rotate your head. And so it's got to be an outward pointing slope. And that's what this means. This portion here means outward pointing. Okay, so we also saw that if you have an electric current flowing through a wire, that it will create a magnetic field that circulates around. And so we need to have a way of describing what does it mean for something to circulate around something else. And that's given by this combination. So this is the slope, and this is in the perpendicular direction. So this is perpendicular, or circulating is another. So this is the perpendicular sign, right, from geometry. That was perpendicular and this was parallel. So it's a slope, or it's a slope that is curling around. So this is actually called the curl, where the other one was called the divergence. So it diverges out from a point. This one curls around a point. Okay, so what happens? If you have a current flowing through some wire, then that's current is given by J because I was already taken. Anyways, current's given by J, and an electric current, a moving electric current, so this is moving electric charges from your perspective in your reference frame, will create a curl in the magnetic field. So here's a curl of a magnetic field, and that is created by this electric current. So currents create that. Another way that you can create a curl in a magnetic field is if you change your electric field. So you have an electric field and you change the electric field, you oscillate it from one side to the other, you can also induce a curl in the magnetic field. Okay, so it's a little bit more than this. This is the electric current. A static electric current flowing in a particular direction will create a curl in a magnetic field. But also a changing electric field. So I have an electric field and I change it, then I can induce a curl in a magnetic field. I believe it's a plus sign here. I'm pretty sure that this one has the plus sign. There's another one that has a minus sign, which I think is the next one. Okay, so the final one is that you can create a curl in an electric field. You can create an electric field that circulates around, and I think I got this right. I can never remember the signs. I can just remember that they exist, and then you look up the signs on the interweb. So I can create an electric field that curls in a particular direction. That's what an inductor does, right? It creates a voltage by having an electric field curling in a particular direction, or resisting the curl of the electric field from a particular direction. So a curl in the electric field, in that case, it's minus a change in the magnetic field. So this is basically the thing that this is an inductor right here. This says that you have a magnetic field in some location, and if you try to change that magnetic field, then it creates an electric field that opposes it, and the electric field that opposes it is circulating around some axis, the axis of your magnetic field. So if I have a magnetic field in some particular direction, and I try to change that magnetic field, I will induce an electric field that curls in a direction that resists the change in the magnetic field. Well, if I happen to have a bunch of wires that are going along the direction of that curl, then if I try to change the direction of the magnetic field, it will induce an electric field that opposes the flow of the current that's changing the electric field. And this minus sign right there, that means opposes. Right? So if you have some stuff, if you have a magnetic field and you try to change the direction of the magnetic field, it will be opposed by the introduction. That changing magnetic field will induce a curl in an electric field, and that curl goes directly along in the direction of the coiled wire. So that's kind of cool. And that's it. Those are Maxwell's equations. There are 4 of them. They are that electric charges create a divergence in the electric field. And there's some constants in there like C's and rhos and mu naughts and stuff like that. But they're not that important. Okay, so that's the electric charges. There is that, as far as we can tell, there are no magnetic monopoles, so this is actually equal to 0. We have that if you want to create a magnetic fields will curl in a particular direction that is based upon either the existence of a current or the change of the electric field in some direction. If you change the electric field, then you'll get a response in the magnetic field. And by the same token, if you change a magnetic field, then you will induce an electric field that goes in the opposite direction. That's what these 4 equations describe. Now, I've very recently, as in like only in the last couple weeks, discovered something that I didn't know existed, but I even checked out a textbook that's behind this green screen right here, that's called geometric algebra. And so these are the 4 Maxwell's equations. 4 Maxwell's equations. In geometric algebra, it's another way that you can formulate physics that looks really interesting, as in maybe even more intuitive than what we currently have. To the extent that what we have here is already intuitive, there might be an even more intuitive way of describing physics. And the result of that is these 4 equations get simplified. These 4 equations get simplified into one equation, and that one equation is that the change in the electromagnetic field is equal to the current. So with this geometric algebra, there's a way of representing all 4 of these equations as one single equation. And that's pretty cool. But I haven't learned enough about this geometric algebra. It might take me a couple of years to kind of dig my way through it. But there are videos online where people talk about geometric algebra. They're usually pretty thick in terms of like the amount of time they spend on, this is the wedge product and here's what it means. But it looks pretty promising. I plan to spend some time on it because it might clear up a bunch of topics in introductory physics that I think would be useful to clear up. Anyways, question. Does the generated current interact with itself, or does it envelop the whole system in a cylinder-like manner? So the generated current from I'm missing where the generated current is coming from. So like the generated electric field here. So if you change the magnetic field, then you get a curl in the electric field. But notice that, so this is time dependent. So you change the magnetic field, then that will induce this curl in the electric field. But that's also a time dependent curl in the electric field, right? I mean, this implies that there's a dependence on time. And if there's dependence on time on one side of the equation, there has to be a dependence on time on the other side of the equation. So there's a time varying electric field. Well, if there's a time varying electric field, then that implies right here that there is also a time varying magnetic field. So the time varying electric field will induce variations in the magnetic field, and the time variation of the magnetic field will induce variations in the electric field. There's some constants in here. Like I mentioned that there's some multiplicative constants that I've ignored. I think that's mu naught J, and there's probably like 1 over C squared here. Anyways, if everything's set equal to 1, then you don't have to worry about that. So this relationship, these aspects of it, the fact that a time varying electric field or a time varying magnetic field will induce a change in its counterpart, that's where electromagnetic radiation comes from. So classically speaking, so Maxwell's equations are classical equations. They're not quantum equations. So this isn't quantum mechanics. This is the classical fields, just similar to, like, general relativity is a classical field as well, classical theory as well, where you have, here's a space-time and you send waves across that space-time by manipulating how it's perturbed. Same thing goes with these ones. So that is electromagnetic radiation is the relationship between these quantities, not this current. That's a static current. You can imagine if you had pure magnetic monopoles. So I mentioned before, if you had actual magnetic monopoles right here, so that you could get a row magnetic, you could have a density of a bunch of north poles that you just pull out of your pocket. It's like, here's a bunch of north poles to magnets with no south pole counterparts. You would also get a curl in an electric field. So there would be another term here that is related to the magnetic current. So you could, if you can get isolated magnetic north poles, you can send them down a wire, and that would induce a curl in an electric field by itself. So that's pretty cool. So going back to this, weird question, but if you cut a bar magnet in half, each piece has 2 poles, so that what point in the bar magnet does one pole say N transition to the other one S? It doesn't. So that's a good question. So the question is, I have a magnetic field like this. I have a bar magnet north and south. And at what point, like when does it actually transition from one to the other? Well, a bar magnet is actually composed of, or a bar magnet comprises several individual parts, right? You have a whole bunch of magnetic atoms in there, atoms with a magnetic moment attached to them, and they're all lined up. And so when you break this down to its fundamental level, you get down to the atomic level, and an atom will have a north and a south pole because of a circulating charge of some sort, whether that charge is coupled to the spin. So you can develop a magnetic field from the spin of the valence electron, or you can get it from the orbit of the valence electron. So both of those things can be the circulating current that you need. But because these things aren't physically spinning and they're not physically orbiting, it's the angular momentum that you get from either the orbit or from the spin. I mean, these are names that we assign to what's going on there. You assign this angular momentum to these things, and that creates the magnetic dipole. And it's the sum of all these individual magnetic dipoles that create the macroscopic bar magnet. So there's no way to slice it any smaller. You get down to a single electron. A single electron all by itself will have a magnetic dipole moment. And that comes from the electron's intrinsic spin. So it's an intrinsic property of the electron that creates a magnetic dipole. And the electron's a fundamental particle. You can't split it up. As far as we can tell, you can't split it up. All right, let's see. Maybe a weird question, but let's see. Maybe a weird question, and I haven't studied math at any higher level. And by the way, so maths, when you hear someone from Great Britain talk about maths, I figured out, well, I was told by one of my counterparts why the British people call it maths and the Americans don't. So in America, we say math. We do math. And in Great Britain, they do maths. And the reason is that the subject is mathematics. It's already plural. So we say math, and they say maths because mathematics is a plural word. And now you know. And now you know why the British have the extra S at the end. All right, so here we go. Weird question. Haven't studied maths at a higher level, but isn't change usually symbolized with delta, which is a triangle pointing upwards and not downwards? That's a great question. So his question is, or the question is, this delta, which is usually like P2 minus P1, is equal to delta P, something like that. So that this would be considered a macroscopic change. So that's a finite element change. If you're talking about an infinitesimal change, then you would use a little delta. So you'd have P2 minus P1, but this would be infinitesimally small, then you would say that that's a delta P. And if you have, so this is a one-dimensional delta like this. If you have 3 dimensions and you want to account for these small changes in all 3 dimensions, then you use del. So this is the 3D version of the small delta. And thank you for that gift. I appreciate that. Let's see. But they work. Oh, and so that's why. So this is the upwards pointing delta is a macroscopic change. The downwards pointing del operator is a 3-dimensional microscopic change or infinitesimal change. All right, let's see. Trying to understand. Oh, okay, but they're working on monopoles. So there are people who are doing experiments to try to find magnetic monopoles, or to constrain the presence of magnetic monopoles, but that hasn't been found yet. You'll know when it gets found because it'll make international news. Trying to understand the implications of the second equation. The slope of the magnetic field is 0. So that means the magnetic field is a constant in tension. Okay, so fresh cow. Here is the question is trying to understand why this equation, del dot B equals 0. So this says that you cannot have an outward pointing source of magnetic field, a pure outward pointing source of magnetic field. Another way to visualize this is if you have some volume, any magnetic field line that comes out of that volume, so the presence of a magnetic field that leaves a volume has to loop around and come back into that volume somewhere else. Because there's no such thing as a source of a magnetic field that would cause something to point outwards in all directions. Okay, so this says there's no sources. No sources of a magnetic field. Or there's no charges. There's no magnetic charge, is what that one says. Let's see. Is it possible to be colorblind to red? That's a good question. It's not particularly relevant, but we'll take a brief tangent and go over it. Is it possibly colorblind to red? Probably, because the way that your eye works is that you have 3 different cones. You have 4 detectors in your eye. You've got red cones, green cones, blue cones, and rods. And the rods detect basically all wavelengths of light. But if you look at the response, like the sensitivity of your eyes to different wavelengths, you've got blue like this, you've got green like that, and you've got red like this. These two overlap each other. If they overlap too much, then you can't distinguish between red and green, and you are red-green colorblind. You can have situations where, like you say, you don't have blue cones, that your blue cones don't work, or your green cones don't work, or your red cones don't work. In which case, you don't have the ability to track all the different colors. So the way that you can tell that something is like here, has that color, is because it's emitting light in some band, and you excite the green cones and the blue cones, and so you get a mixture of green and blue, and you say, that is, whatever color this happens to be, turquoise. Q-U-O-I-S, turquoise. Or if you have something that's orange, it's actually a mixture of green and red, and so it emits light here, which means that both the green and the red cones are firing. So you can imagine having red cones that don't work for some genetic reason, your body doesn't produce them, or green cones or blue cones. The most common color blindness, which is almost always in men, like 20-to-1 in men, is that I believe what's going on is that the sensitivity curves of these two things overlap too much. And so you get 2 curves like this, and you can't distinguish between the two. And so those glasses that help you distinguish between red and green actually put a notch filter in here that don't allow those colors to pass. And so it separates the place where the confusion happens and allows you to see the difference between red and green. And so where red and green overlap is in the orange, and so that's why they look orange, right? So that's what's going on. Okay, let's see. Where did we get to? So we talked about Maxwell's equations. That got us there. So all these things, Lenz's law, motional EMFs and stuff like that, transformers. So this gets us to, we did electromagnetic waves in general. Oh, a few things about electromagnetic waves that are interesting. So electromagnetic waves. Electromagnetic waves are waves of electric and magnetic fields. We know from Maxwell's equation, so if we just look at the oscillating part, we're not worrying about electric currents, we're just looking at the oscillating part. We get this del cross E, what equals minus B dot, and del cross B equals E dot. Okay, so the time derivative of the magnetic field gives you the curl in the electric field, but the curl is always perpendicular, right? So if you change the magnetic field in some direction, the curl indicates that it has to be something perpendicular to it, because if you have a wire, the flow of electricity in the wire goes this way, but the curl is perpendicular to the flow. And so this curl here is also perpendicular to the change in the magnetic field. So if you have this thing that's oscillating, the magnetic field will be changing in some direction, like yay, and the electric field has to be changing in a direction that is perpendicular to the magnetic field. And so these things are going to be like yay. So you get, when one of them oscillates in one direction, the other one is oscillating in the opposite direction. They don't necessarily have to be in phase with each other, like exactly in phase with each other. But the changing electric field and the changing magnetic field are always, the electric and magnetic fields are always going to be perpendicular to each other. And that's given by these equations right here, because this says it's changing in some direction and the response to the electric field is in a perpendicular direction. The curl is in a perpendicular direction. Let's see. So this is, I guess, something useful to point out. What did this have to do with anything? Oh, the direction that this is moving, the direction that this electromagnetic wave is moving is perpendicular to both the electric field and the magnetic field. And it carries energy with it. Waves can carry energy. So this carries energy with it. And so the direction that the energy and the momentum move with with an electromagnetic wave is in the direction what? So if this is B and that's E, then it's going to be B cross E. So I think it's called the pointing vector. The direction is B cross E. I think this is right. We might as well look it up just to make sure that it's exact, that is actually what it is. All right. So, and then I got some questions coming up. So if I go pointing vector, the pointing vector is, oh, E cross B. I was wrong. I got it exactly wrong. So the pointing vector is the direction of this motion is E cross B. So it's perpendicular to both E and B. That is J. Not J, that's S. That's the pointing vector. And there's probably a mu naught in there or something like that. There's probably some constant, fundamental constant that you multiply out front. Okay, why is this important? This is important because this is the direction of the energy flow. Energy moves in the direction E cross B. And I will show why this is important in a moment. But before we do that, let me come back to some of these questions that are here. If you want to study physics, practice problems. That's what you do. Would two opposing direction currents fields nullify each other's fields? Yes. So fields add. And so if you have two electric fields that are opposing each other, then they cancel each other. The reason for that is that the fields themselves are not the fundamental thing. The fundamental thing is the potential. And so if you have one potential that that looks like this and another potential that looks like that, so that the sum is going to be some flat thing, then there's no gradient and there's no field. Anyway, so that's what's going on there. Then we need at least three-dimensional space to have electric and magnetic field, the direction they are propagating. In a 2D universe, it wouldn't work. I think that's right. I think that in order to get an electromagnetic field, you have to have a three-dimensional universe. You cannot get a two-dimensional universe out of the electromagnetic field. And actually, when I was in graduate school, I don't know how much stock to put into this, but when I was in graduate school, someone actually suggested, and it was a smart guy, that the reason maybe we perceive a three-dimensional space is because we have E, B, and E cross B as the three perpendicular directions, and all of our senses are based upon the electromagnetic field, right? All five of our senses are manifestations of the electromagnetic force, and sight in particular is a manifestation of the electromagnetic force. So I don't know how deep that is, but it's certainly curious that you must have a three-dimensional field in order to get electromagnetic waves propagating in a particular direction. Now, to the photon itself, it doesn't see the third dimension, right? The photon doesn't realize that it's propagating. To the photon, everything is all happening instantaneously. So that also, maybe has implications for perhaps the third dimension is actually not that important. The direction that the photon is moving might not be important, and actually that we only need a two-dimensional universe, and so that's where you get the holographic principle. It's motivated for other reasons, but that maybe we're actually living in a two-dimensional universe and we don't need to have three dimensions to describe everything that's happening. Okay, so let's see. There is it physically possible to change the angle between the electric field and the magnetic field? So not in an electromagnetic wave. So if you have an electromagnetic wave that's moving like this, the electric field is oscillating up and down, the magnetic field must be perpendicular. It doesn't have to be in phase with it. So these nodes don't all have to happen at the same time, but they do have to be perpendicular. So you can have something set up where you have an electric field that's oscillating like this, and the magnetic field is oscillating like that. Okay, so the magnetic field oscillates in a direction that is, it's still perpendicular, but it's perpendicular and its phase is retarded. So its phase is delayed relative to the electric field. So what that does is, what you get from something like this is a circular polarization. So if they're lined up, then you have a linear polarization, and if they're not lined up, then you get a circular polarization. Let's see, do you teach the right hand and left hand where your thumb is the current direction to help with this? The right hand and left hand rule, I always use right hand rule. Left hand rule is for losers, in my opinion. Okay, so let's see, there was something else that I was going to discuss. Oh, yeah, so the pointing vector. The pointing vector is the direction of the flow of energy. So the pointing vector is E cross B. And this is the direction of the flow of energy. So if you have an electric field oscillating like this and the magnetic field's oscillating like that, then E cross B, the way that works is you point your fingers in the direction of the first one, you curl them in the direction of the second one, and then your thumb points in the direction of motion. So E cross B, another way to think about it is, that's going this way. So E is up, B is this way, so that curls this way, which points, if that is counterclockwise, then that means that this must be the direction that it's moving. So that's moving in this direction. So that's the direction of the flow of energy. Now, consider what happens in an electric circuit. So you have an electric circuit. Here is an electric circuit, like, let me draw it with a battery in it. So here's an electric circuit like this. Okay, and you've got some resistor on it, some device connected to it. And so you've got energy that's flowing this way. Or you have an electric field, I should say. You have an electric field that is pointing around this thing like that. Okay, because you have, a positive side here and negative side here. So the electric field is pointing like this around that wire. The magnetic field is curling around the wire. So there's the magnetic field curling around the wire. So at this location right here, which direction is the energy flowing? Which direction is the energy flowing? Well, the electric field is pointed this way. The magnetic field is going to be pointed that way, right? So these, I guess I'll connect them together at that single point. So it's projected above it because I'm considering like the magnetic field up here. But the electric field is pointed this way. The magnetic field is pointed that way, where these are 90 degrees apart from each other. And so E cross B is pointed that way. So at this location, the pointing vector, S, is pointed inwards. And if you consider it from just beneath, from just below, then E is also this way, B is now into the board. So from below, you have E this way, you have B pointing that way because it's curling around, which means E cross B gives you that direction, inwards. So the energy in an electric circuit is actually flowing into the wire. The electromagnetic field is providing energy into the wire, not along the wire. That's weird. So here you have the circuit going around. There's energy that's being supplied to drive it, and the energy is coming from the electromagnetic field surrounding the wire. The electromagnetic field is everywhere, and you're causing, like the presence of these voltages and stuff like that is causing a disturbance in the electromagnetic field, and it's providing energy to the circuit, and the energy is coming from the electromagnetic field that is surrounding the circuit. So that's pretty cool. S measures, S is not the current. S is measuring the direction of the flow of energy. So the pointing vector is the direction that energy is flowing. So S is E cross B. So when you have a photon, like electromagnetic radiation, it tells you the direction that the photon is traveling, the direction that the wave is traveling. Is there a unit associated with it? Yeah, it's got units of energy. I think there's a C in there probably, or a mu naught, something like that. So the pointing vector has units of energy. Is it energy per time? I guess I pulled it up already, so let's see. Because E squared, B squared, those are related to each other. Excuse me. Okay, here's a DC circuit showing the battery and the pointing vector S in blue arrows. So you can see that the pointing vector is pointing outwards from the battery. Okay, so this is looking at the macroscopic. This is looking at the macroscopic circuit, like the whole circuit at once, and not just a portion of the wire. So this is the sum of all the components that are contributing to it. So, anyways, it's going out of the wire. Various components will cancel on either side of the wire, and then it goes into the resistor. The pointing vector does. So is there, I think it has units of energy. So yeah, once you get all the factors in there, then it has units of energy. Which this one got convoluted a bit. Yep, it probably did. Anyway, so that is the pointing vector. That's how energy flows from electric circuits. Let's see if there's anything else with electric circuits that we need to talk about. I guess I can talk briefly about other things related to electromagnetic waves that are important in particular. So we're looking at a photon. A photon is approaching towards us. A photon is coming towards our eyeballs. Okay, that photon is going to have an electric field. Here is the electric field oscillating up and down. So the electric field is coming towards us and it has some oscillation. The electric field is oscillating up and down in some direction. You could have a photon coming towards us where the electric field is oscillating like this. The point being that when a photon is coming towards you, you have a two-dimensional plane in which the electromagnetic or the electric field can oscillate, and the magnetic field would be oscillating perpendicular to that. So the magnetic field would be this way, the electric field would be some way. So we have to choose how we define our coordinate system. If we want to describe what is the direction of oscillation of the electric field, then we need to have a way to place a coordinate system on it. Okay, if we want to describe it, especially since we have a two-dimensional plane, we have to have a two-dimensional coordinate system to say, oh, here's where that electric field is oscillating, here's where this electric field is oscillating. And so that gives you two choices. So you're going to impose your own coordinate system onto this system, onto this photon that's coming towards you. And you're going to say, okay, this is one direction, and a perpendicular direction is the other direction. And we talked early on about why you would choose two directions that are perpendicular to each other, because then they're independent from each other. Okay, these are the two polarizations. So the two polarizations that a photon can have is not because there's two magic polarizations. It's because the photon is coming towards you, and that corresponds to a plane, and you have to be able to describe the orientation of the electric field in a plane, and therefore you need two coordinates. And so we assign those two coordinates to different polarizations, vertical or horizontal or whatever. But if we chose a different coordinate system that looked like this, you know, what directions do you want to assign to those? It doesn't really matter. The point is that you have to have, there are two independent directions that you need to describe the orientation of the electric field as this photon is coming towards your eye. So there's nothing special about vertical and horizontal polarization. That's all a social construct. Vertical and horizontal electromagnetic polarization is a social construct. The fact that there are two polarizations is not a social construct, because we're talking about a two-dimensional plane that's coming towards us. Now, if the electric field and the magnetic field are out of phase with each other, then what you end up with is that the how does this work? So there's some vector that over time oscillates around like this, and that oscillation is either clockwise or counterclockwise depending upon what the relative phase is between the electric and the magnetic fields. And so those are circular polarizations. I think the way that you construct those is that you say another way of getting something to oscillate straight up and straight down is to say, oh, so I have something oscillating straight up and straight down. And we've already talked about oscillations that are straight up and straight down and how they relate to circular motion. So an oscillation is going to look like cosine omega t or something like that. Okay, where omega is the oscillation frequency in radians per second. So you have something that oscillates up and down. This can be, a vertical oscillation can be deconstructed into oscillations in two different directions. And in that case, what you look at is you say, consider something that's circular going like this, okay, and something that's circular that's going in the opposite direction that is exactly equal and opposite, which is not what I drew. So that's a little bit better. So this one's going this way, this one is going this way. And then what's going to happen, if they're oscillating in opposite direction, or if they're circulating in opposite directions, then the component that is sideways, when this one is moving that way, the components that sideways and the components that sideways here, those are going to cancel each other. So if you have these two circles that are going in opposite directions and you put them on top of each other, the sideways components will cancel and the vertical components will add. So you have two things going in opposite directions. The sideways components cancel, the vertical ones add, and as a consequence, your response is a vertically oscillating sum. The sum is vertically oscillating. Or if you get them oriented so what happens? So this is if they're in phase going up and down, then you get this vertical thing. If they're in phase so that the phase coincides with this direction, then you can get them to oscillate side to side instead of up and down. Okay, so how you add these things together, where you start the sum, will determine whether you get a vertical polarization or a horizontal polarization. Okay, so one way to decompose a linear polarization is into two counter-rotating circular polarizations, and vice versa. So it's just another way of representing a vertical plane. So you have a vertical line that's oscillating up and down. You can say, oh, that is actually the sum of something that's oscillating up and down is the sum of something that's going cosine omega t and something that is going cosine minus omega t. And you add them together and you get something that just oscillates in a single direction. So it's another way of mathematically decomposing the system. You can either decompose it into horizontal and vertical polarizations, or polarizations that correspond to one axis or another, or to some rotation in space, or its opposite. Okay, so this is actually how 3D movies work. So 3D movies, what you could imagine doing with 3D movies, in order to get in order to get a 3D movie to work, you have to produce a different image in your right eye than you get in your left eye. Your two eyes have to see different images. So with a regular movie, you just have, here's your screen, you have unpolarized light, hits the screen, bounces off, comes to your eye from all these different directions, and both eyes see the same image. And so you get no depth perception. You can only infer the depth based upon the relative sizes, like what you understand about perspective. If you actually want to see in 3 dimensions, you have to have different images in each eye. Each eye has to have its own image. So one way to do that would be to have one camera that shines in blue light and one camera that shines in red light, and the two images are separate from each other based upon how deep in the field that object is. So if it's a very deep object, then you give it, then the red image and the blue image are on top of each other. If it's something that's really close to you, then you would separate the red and the blue image. And then what you would do is you'd wear glasses that have, so here's your glasses, special glasses, where this one is colored blue and this one is colored red. And so that the blue one is only able to see the blue image and the red one's only able to see the red image. And so then your eye gets two different images. Okay. A challenge with that is if you rest your hand on the side of your head like this, the images are going to be displaced side to side. So you have a blue image here and then a red image that's slightly displaced from it, and that would imply that this object should appear close to your eye. But if you turn your head to the side, so if you like rest your head on your date's shoulder or something like that, then these images no longer work, right? The three-dimensional aspect of it goes away because you have to have the glasses lined up with the two images. The glasses have to be lined up with the two images, and then when you turn your head, it doesn't work. Another way you could imagine doing it is, I think that's going to be true with any of these things. Is that right? Well, anyway, so another way that you could imagine doing this is that you have one glass, so you have light shining off the screen from two different polarized light sources, and then you have glasses that look like this, where one of them is only able to see vertically polarized light and the other one's only able to see horizontally polarized light. And that way you can get the two images and see in 3 dimensions, and you don't have to have one image be blue and one image be red. So your eyes detect the correct colors, and you're only using polarization to produce a different image in each eye. So that's another way to do it. A challenge with this is that it doesn't, if you rotate your head, then you're actually rotating one polarization into the other polarization. And so I guess with the red and the blue filters, so we've all seen these things like the 1950 style 3D glasses, red, blue. So these are the red, blue 3D glasses that you could do with that original thing. And these go back a long ways. With a polarized one, the problem you have with a polarized one, so even with red and blue, what would you get? You would still get a different image in each eye because they're both displaced. So I guess it would work. I'm going to retract my earlier statement and say that if you had red and blue, then and you rotate your head, you would still see two different images. With these polarized light, however, if it's linearly polarized, then you run into the problem that if you rotate your head, then you're actually rotating one polarization into the other polarization, and it doesn't work anymore. In fact, the whole thing would start getting darker because the light can't make it through either of the filters very well. So instead, what you do is you would make you'd make glasses like this, where this one is polarized counterclockwise polarization, and this one is polarized with clockwise polarization, because these things don't change. So you have the two circularly polarized lenses, and then when you rotate your head, the polarization stays the same. Where with linear polarized light, if you rotate your head, then you have one that's polarized this way and the other one that's polarized this way, and those are both oriented at 45 degrees relative to the light that's coming off of the screen. And so the screen will go darker as you go this way, and then if you keep turning your head, then the eyes will actually switch. Which eye is seeing which polarization will switch. But with circularly polarized light, so these glasses, as you rotate your head, the circular polarization stays the same. It doesn't matter because that's a direction of rotation and not an orientation in a plane. So that's how you can make three-dimensional glasses that will work regardless of how you tip your head. Another thing to point out is that LCD screens, liquid crystal displays, those are long polymers, long chains of stuff that allow electrons to flow only in a particular direction. So electrons can't flow side to side; they can flow along the line of that long molecule. And so if you oscillate the electrons in these molecules, they act like antennas, and they only allow light to propagate that is with the electric field aligned with the direction of how the molecules are laid out. And so liquid crystal displays emit polarized light. And if you go to a gas station, if you're wearing polarized sunglasses that are designed to cut down on glare, if you're wearing polarized sunglasses and you go to a gas station, if you rotate your head, if it has a liquid crystal display and you rotate your head, you can get it to turn off basically, because you can align the glasses so that it eliminates this polarization. You turn your head and then it eliminates that polarization and the screen goes black. And then you rotate it back, and then you rotate back into the polarization that is allowed to escape. Typically, the way that they will orient the LCD screens is so that it accepts probably the horizontal polarization. No, it would be oriented so that it accepts the vertical polarization, and your sunglasses typically have the polarizers eliminate the horizontal polarization. See, it eliminates the horizontal polarization, so your eyeglasses will also be vertically polarized. So your sunglasses will be vertically polarized because you want to eliminate the horizontal polarization, because the light that comes from glare off of the hood of the car or off of the water on the lake is going to be horizontally polarized. So that's how that works. Okay, that's all the time that I got for today. Let me answer whatever questions are left, and then we'll have to declare victory. What do we got coming up next in this? So we talked about, so we'll be doing optics next is what it looks like. So optics, okay, so that should be cool for a bit. Do some optics. And then we'll get into the really cool stuff at the end. We'll get into relativity. We'll talk about atomic physics. We'll talk about nuclear physics, and more nuclear physics, and then particle physics, and that will be it. So how much more time do we got? We probably got, I don't know, maybe about a month or so, month-ish worth of material left in this series, and then I'll have to think of something clever to do. I do have some guests, at least one guest lined up. Probably get a second one lined up here pretty soon. So anyways, let me answer the questions that we have going on here. Let's see. onboard a photon experiences 0 time, so it does not have oscillation of its own reference. On board a photon, it experiences 0 time, so it does not have an oscillation in its own reference. Okay, maybe that's an incorrect statement that I made, that it doesn't experience time. It doesn't experience the forward direction. It doesn't experience forward. So it can still experience side to side. It just sees the whole universe in front of it, like simultaneously. Let's see. If the polarization photon is subject, how does the polarizing filter polarize it exactly? If the okay. So how does a polarizing filter polarize it? What that does is what a polarizing filter does is it says, okay, the light's coming in with some polarization, some angle like this. Okay, an angle with respect to what? Well, angle with respect to what I choose to be my coordinate system. But then I have a polarizer that is also oriented at some angle with respect to my coordinate system. And so what light so this is the photon here, and this is my polarizer lens right there, or my filter there. They're both with respect to some coordinate system. And so if I choose vertical and horizontal to be my coordinate system, then I would choose vertical and horizontal to be the polarizations that I would consider. And then basically what you do is you say, how much does this thing oscillate in this direction? And you say, okay, so it's got components. This electric field has components in this coordinate system. And the component that is vertical is the portion that will make it through, and the component that is horizontal or perpendicular to these lines will not make it through. And so then you just say, okay, so I have a component here and a component here. This one goes to 0, that one persists, and that's how I get the polarization state that comes out. So it would be like, I have this electric field oscillating. It's got some component in the vertical direction. If I choose vertical to be my vertical and horizontal to be my polarizations. Suppose that I had this thing and I wanted this to be one polarization and this to be the other polarization. Then it would be 100% polarized that way and 0% polarized this way. If I choose vertical and horizontal, then what I would do is I would say, okay, what are the components that are in this direction or that direction? And that would be like, if say it's coming in at 45 degrees, it would be 1 over root 2 vertical plus 1 over root 2 in the horizontal direction. And then I say, I only care about, so another way to write this would be like 1 over root 2, this is a root, and that's a 2. In the vertical direction, which would be like v hat, and then plus 1 over root 2 in the h hat direction. And then I dot that, so this is my photon. And I want to go photon dot which direction I care about. I care about the vertical direction. And so that will mean I get 1 over root 2, what, squared? So the probability would be this thing squared. And so I get a half. So the amplitude would be 1 over root 2. The probability or the power would be the square of that. So that's the amount of energy that gets through. The amplitude of the wave that comes through would be 1 over root 2.